Hello everyone. In this video, we are going to see DC to DC boost converter. It is a step-up converter. The output voltage is equal or greater than the input voltage. There are two modes of operation. In mode 1, the switch is in the on condition, and in mode 2, the switch will be in the off condition. The circuit of the boost converter is shown here. The circuit consists of L, switch, diode, capacitor, and the load. The switch is operated with a duty ratio of K is equal to T on by T. The various applications of boost converter includes it is used in battery charging, power amplifier, automotive, heaters and welders, adaptive control, power factor correction, and DC motor drives. The modes of operation in mode 1. During this mode, the switch S is in the closed condition and the diode is in the open condition. During this mode, the current flows from the source Vs through L and back to the source. During this mode, the inductance stores energy in it. At the same time, the capacitor dissipates its energy to the load. In mode 2, the switch is kept off condition and the diode is in the on condition. During this mode, the inductor energy, which was stored earlier, it is dissipated, and during this time, the capacitor is charging. The various waveforms for the boost converter during mode 1 and mode 2 are depicted here. The first waveform shows the PWM signal. The second waveform shows the inductor current, which rises from minimum value to a maximum value during the mode 1, and it falls from maximum value to the minimum value during mode 2. Then the third waveform shows the source current waveform, which is same as that of the inductor current waveform. Then the fourth waveform is the diode current waveform. Then fifth waveform is the capacitor current waveform, and the last one is the capacitor voltage waveform. And now let us write the voltage equation of an inductor during the mode 1. In mode 1, we can write VL is equal to Vs, and VL again can be written as L into DIL by dt. And DIL is nothing but delta I, which is I max minus I min, and dt is nothing but T on. So L into del I by T on can be written as Vs. Again, this L into del I by T on can be substituted. Instead of T on, we can substitute KT, where T on is KT. So L into del I by KT will be equal to Vs. And from this equation, we can write the expression for del I, which is equal to Vs KT by L. Also, we can write the expression for KT, which is del I into L by Vs. Again, during the mode 2, we can write the voltage of the inductor in terms of Vs minus VL equal to Vs minus L into DIL by dt equal to V naught. And during this time, DIL will be equal to I min minus I max, because the current falls from I max to I min. So that DIL will be minus del I and dt will be T off. So minus L into del I minus del I by T off can be written as V naught minus Vs. Rearranging the terms, we will be getting L into del I by 1 minus K into T equal to V naught minus Vs, as T off can be written in terms of K as 1 minus K into T. And from this, we can write del I is equal to V naught minus Vs into 1 minus K into T divided by L. Also, we can write 1 minus K into T, that is T off, equal to del I L by V naught minus Vs. And to derive the output voltage, we need to equate equation 1 and 2. So equating 1 and 2, we will be getting Vs kt by L is equal to V naught minus Vs into 1 minus K into T by L. Simplifying the above expression, we will be getting the output voltage expression as V0 is equal to Vs by 1 minus K. Now we can derive the ripple current expression. We know that time period T is equal to T on plus T off, which is Kt plus 1 minus K into T. Substituting for Kt and 1 minus K into T, we will get T is equal to this one. And from this expression, after rearranging and simplifying, we will get del I is equal to Vs Kt by L, or we can get del I is equal to Vsk by Fl, where F is 1 by T. From this expression, we can get the expression for L as Vs into K by F into del I. Now, the ripple voltage can be found as del V is equal to Vc minus Vc of 0, which is equal to 1 by C integral Ic dt plus Vc of 0 minus Vc of 0. And we can integrate this Ic during the on period. And during the on period, we know that Ic is equal to I naught. So magnitude of Ic is I naught. So del Vc is equal to I naught T on by C. Substituting for T on as Kt, you will get del V is equal to I naught Kt by C, and which in turn can be written as del V is equal to I naught K by Fc. From this, we can also get the expression for C as I naught K by F into del V. Now we will derive the condition for continuous conduction. In order to have the continuous conduction mode, the capacitor and the inductor value should be more than a particular value known as the critical values of L and C, which are denoted as LCR and CCR. To obtain LCR and CCR, to obtain LCR, we have to equate the ripple current to 2 times the load current. And to obtain CCR, we have to equate the ripple voltage to 2 times the load voltage. So derivation of LCR and CCR is shown here. Del I is equated to 2 times load current. So del I is equal to Vsk by Fl is equal to 2 I naught. Now substituting I naught as V naught by R and rearranging, we will be getting the L value, which is nothing but the critical value of inductance as Rk into 1 minus K by 2F. And similarly, we have to equate del V equal to 2 V naught to get the CCR expression. And substituting for del V as I naught K by Fc, and I naught again, if it is substituted as V naught by R, we will be getting the CCR value as K by 2RF. In order to operate the converter in the continuous conduction mode, the values of L and C should be chosen greater or equal to the critical values of L and C. Here R denotes the load resistance. Thank you.